The beginnings of rotational motion should feel very familiar to you for the following reason. Just about for the whole class, we've been working on these two equations right here that describe how the position, velocity, and acceleration of a vehicle are related between the vehicles to, say, points in time. So, for instance, at one time the car could be here at some position x naught with some speed v naught, and a time later it could be here at some position x with some speed v. And during the time interval, it has some acceleration on it, which moderates the motion of the object. And the position here, the x naught and the v naught and the x and the v are related by these two equations here. So it turns out when you start talking about rotational motion, you're talking about very much almost the exact same stuff, only things aren't moving straight down roads. There's no more linear motion anymore, like a car or a ball falling. So another example that you might have worked is a ball here that might be falling above the ground in some linear motion with some speed v and perhaps some height above the ground. These are all examples of linear motion where, say, the acceleration on the ball in this case is g, or the acceleration of the car over here is some a, and they're always related by these two equations right here, which we've been using all quarter. So again, hopefully you have some familiarity with that. Rotational motion comes in when it's no longer things are moving straight down roads or falling straight down in columns of air or something, but now they're rotating. And as an example of that, you could think of something like a fan blade that might look like this. So here's sort of a fan blade here, and just think of it as spinning now. And one thing you might want to know is, say, if there's a dot on the fan blade right there, you might be interested in, well, where is the dot at some time in the future? Is it going to be over here or over here or over here? And of course, as you might guess, where that dot's going to be is a function of how fast the fan is spinning, what the acceleration of the fan might be, and that sort of thing. So we have an entirely different set of parameters for something that rotates, because you should agree that the fan blade is moving. It's rotating. It's just not, say, going down the road. So it doesn't go very far. It's always in the same position. But there is some motion there which needs to be described. Another example could be something like a wheel of a car like this. Something that you might just see on a car like that. And there might be some writing on here, like, I don't know, the brand of the tire. It might be in here in some letters or something. And as the tire starts to rotate like this, as it's attached to the car, you might be interested in where the letters of the tires are at some point in the future. Are they going to be, say, down here or down here or down here? Where will they be at some given time t? Just like you might ask, where is the car going to be at some given time t? So it turns out that we have a whole other set of parameters used to describe the rotation here. In particular, we have a variable called theta here, which we call the angular position. That'll sort of be like the analogous to x. X is the linear position where the car is down the road. Well, theta is going to be the angular position. And the angular position of something is very often measured in units like degrees or radians or revolutions. So in other words, if we're talking about where this dot on the fan is, we could say it's so many degrees from the vertical, or so many radians from the vertical, or so many revolutions from the vertical. So that's the angular position, very analogous to the parameter x. The next parameter that you'd be interested in then is how fast is the fan traveling, and that's always given by the symbol omega. So this is not a w. This is the Greek symbol omega right here. And omega then is referred to as the angular velocity. And it's just exactly analogous to v. So where x is the position, v is the velocity, theta is the angular position, well, omega is the angular velocity. So if you go up to the fan blade here, look at the fan blade or the wheel, these arrows here sort of describe, or you might think of as how fast the object is spinning. So we might very well label this arrow here omega, and this label here omega as well. They tell you how fast the object is spinning. And lastly, as you might expect, if you have position, some sort of position variable and some sort of velocity variable, you also have an acceleration variable. This is the Greek letter alpha here, and this is called the angular acceleration. And it is exactly analogous to the a, or the acceleration parameter for linear motion. So once again, here's where the analogy is its strongest, and I hope you can tie all these things together. If a car has a certain position, velocity, and acceleration, that is all you need to know using these two equations to figure out where it's going to be a small dt in the future. Likewise, if something rotating has an angular position, an angular velocity, and an angular acceleration, there are some equations you can use to tie together where the object is going to have rotated through a small time in the future, and say how fast it's going a small time in the future too. And guess what? The equations you use are exactly the same as the ones you've been using all quarter. So in other words, you would definitely write theta is equal to theta naught plus omega 0 delta t plus 1/2 alpha delta t squared, and you'd also have omega is omega naught plus alpha times delta t. The exact analogous equation that you've been using all quarter for linear motion now hold for angular motion too. It's almost like a one-for-one correspondence or analogy between all the linear variables, the x, the v, and the a you've been used to all quarter, and the theta, the omega, and the alpha that are new now for rotational motion. But these are the two guiding equations which we'll use, say, to solve some problems and figure out things about, say, rotational kinematics, as it's called. So just like we have linear kinematics, cars and going down roads and ball droppings and those sorts of things, we also have rotational kinematics, which is where we sort of stop and study, well, questions like I posed before, where would this black dot be on the fan blade a small time in the future, and say how fast would it be going? Likewise for the wheel, where would the lettering on the wheel be? But the analogies also continue with this rotational motion. In particular, if we go on and say things like, in the course we move on and say later, we'd say something like in linear motion that F is equal to ma, force is mass times acceleration. This is one of Newton's laws here, and one that everyone sort of generally walks around and knows. Well, the analogous one now for rotational motion is you know that A is similar to the variable alpha. In other words, linear and angular acceleration are related. But now what about m? What's going to happen to m? Well, m becomes I, which is something called a moment of inertia. The equal sign is still there, and the F becomes the torque. So you see the analogy again here. A is like alpha, m is like moment of inertia, and F is like torque. Now, there's a lot of things to discuss, and there'll be a whole other video on what moment of inertia is, and even what torque is for that matter. But for now, just know that the analogies stick. And part of the description would be, if you know that mass is the linear inertia something has, or its resistance to want to change its state of motion, well, guess what? I, which is the moment of inertia, is a rotatable object's resistance to want to rotate. So they're both resistance terms. This is a resistance to want to move. This is resistance to want to rotate. So they're sort of related in that way. And likewise, where a force here could be thought of as a push or a pull or something like that, that you would apply to an object to get it to go, torque is exactly the analogous quantity here. It's not really a push or a pull, but you can think of it like a force. It is not a force. I'm putting force in quotes, but you can think of it as a force to get something to rotate. That's probably the best way to think about what a torque is, and the relationship is just analogous.